Professor, you are muted.
Okay, this is exactly. Wait. Okay, now should be okay.
Yes, we can hear you now.
There is this green button, so there are plenty of clicks here. Okay, so but you get the point. So from home, I cannot read the chat. I mean, I'm not taking care of that because with the multiple displays, this is something difficult for me to take care of. So just unmute yourself and ask questions, please. Questions are very welcome. So let's try to make this lecture as interactive as possible, and this holds for all these lectures, right? So here is just a few words to introduce myself. The most important thing is that I'm collaborating with Professor Matteucci with this course for a while. We have been teaching this class for a PhD as a PhD course. I was giving a course on image classification. I was giving a course on deep learning, and there was a natural intersection between the two. So that's why then we decided to give. So this course then was, they received a lot of attention, a lot of interest from students, and then was moved to the master science classes, and here we are. I'm still taking care of a part of this, the part of this course which is related to images, because this is my major research interest, image analysis and processing. So I will give like 7 lectures, starting from the very basics of image classification, which is today's lecture actually, and then we will get to maybe to the very advanced topics on deep learning. Okay, so there is my website. There you can find the slides of the lectures. At the moment, you can find last year's slides. I will remove them, upload the most recent slide after every lecture, and you can, together with annotations. Okay, in particular, I will use many annotations during the online lectures, which I will give on Thursday. And that's it. Any question from logistics, from technical aspects, from home, from here? So very simple. I mean, you're used to it. So today, this is a very introductory lecture, but at the same time, we will formulate the basic problems related to image classification, which will be used as a kind of running example for the lectures. I mean, that's a key problem for deep learning. Is probably one of the major driving application scenario of deep learning models. So it's the right topic to start from, and it's the right topic to see why new architectures are needed in order to handle images, in order to classify images. And so let's first give a short introduction to computer vision, and because our solutions will be actually solution meant for computer vision. So the neural networks we will design will find a lot of application in computer vision. So computer vision is an interdisciplinary scientific field that deals with the computer and how this can be made to gain a high level understanding of the visual world, okay? So gaining a high level understanding of the visual world, this is what will be our goal. And this field has like terribly grown over the past few years. But now I forgot to unhide the slides. So sorry, give me just a second. Yeah. And you can see, hopefully I can start the video, yes. And this should be this is an example of how a recent neural network, there is something wrong with videos. The videos in PowerPoint, they do not like me for some reason. I don't know. Sorry. That's really a pity. Okay. Okay, I'm surrendering. There's no video here, but here there should be, yeah. So you can see how a high level, and what does it mean, a high level understanding of the so let me start again. No way. But this was working. I was double checking this, but now it's not. I don't know whether it is due to WebEx or what. This is really, I don't know. So we stick to images, okay? No videos, sorry. No fancy stuff to show. Yeah, no, I will add them. I will add them. And maybe I will include them as a YouTube video. Maybe I will be more lucky. So let me share the content again. I'm having trouble in sharing videos for some reason while giving lectures on WebEx. Okay, so what you can see here, it's what a neural network that is trained for object detection can understand out of a single frame of a video. So you can see there are like bounding boxes drawn around each person, and there is a label up over the bounding box saying that there is a person, saying that there is a traffic light, like here, saying that there is a handbag here for the lady. So this network, it's, yeah, you can see the references, it's YOLO, and can process like a video in 30 frames per second. So this is what I mean by saying there is a high level understanding of the digital images or digital videos. And here is another example of high level understanding of images, of the world from images. You can see all these like skeletons like that are overlapped over persons in the video. So these have not been like manually annotated over there, but these have been rather automatically located there through deep learning, another deep learning. So this is like more recent work, but I mean the field is growing very, very incredibly, and we will see how during this course we will see how this problem can be addressed by deep learning models that we are going to study. So it won't be surprising for you that this stuff is made possible. Maybe you won't be able to do the same because they are kind of very challenging. Say there's also a huge programming activity behind it and programming experience and a lot of training data needed. But still, that wouldn't be something like, okay, I don't know at all how to address this. It will be rather clear how to do this. And it would be very nice to see this video, but now I can just mention that, as you can imagine, these deep learning models find a huge amount of applications nowadays in autonomous driving, or here are a few examples. For example, the analysis of the shelves of like for a supermarket, where you can analyze the shelf and identify each and every product present over the shelf. Like what kind of cornflakes, what kind of um, what product is there. And this is something I'm mentioning just because I'm kind of collaborating a lot with this team from Steam Electronics. These are not only like the most fancy applications you can imagine, but also these models, these deep learning models are growing in popularity also in like more traditional domains like quality control, quality inspection. Okay, so here is our collaboration with the Steam Electronics where we want to analyze silicon wafers. So here is where each and every electronic device was born. This contains chips, memories, sensors. So there are plenty of stuff in here that were from a disk, a wafer like this, and there are like inspection machines that check each and every wafer, and they provide like a map. And it's rather normal to have like defects spread through the wafer. But if you find some like pattern, then this pattern can indicate that there is some issue in the production, like some, for example, in this case, there is some machinery that is manipulating the wafer and it's scratching them, and then you want to analyze, and then you want to stop the production. So now you can imagine you need some automated tool in order to identify these defects. Otherwise, you cannot check each and every. And I mean, this deep learning made this possible, and it made it possible very accurately. I mean, it's being monitored. I mean, I can talk about this is not probably the most surprising one, but this is something I've directly experienced on that. So that's why I'm talking about this. And even going back to the high-level understanding of the scene, you can see here what I mean by image captioning. So this neural network was fed with just a couple of images. Was fed with each of these two images, and what it was providing as output. So this image was the input, and this text was the output. Right? So the text, it's a caption which does make sense, and the caption that can correctly interpret the content of the scene. So gaining a high-level understanding of the visual world by, if you write, little girl is eating a piece of cake from this picture, I think you made it. And these results were kind of unbelievable, like 6, 7, 8 years ago nowadays. And this is CVPR, Computer Vision and Pattern Recognition Conference. And now, and you can see how much the attendance, so the number of participants has increased. Now, of course, I'm not reporting 2000. Okay, I can include 2020, of course, because it was made online. But so you can see the growing interest in this conference in terms of everything, and this is like due to the fact that somewhere between here and here, deep learning has started consolidating. So now, if you go to this conference and you look at the keywords, right? So at the computer vision conference, they are talking about learning. They are talking about networks and detection, segmentation, convolutional, deep are all keywords related to deep learning. So there has been like an increasing connection, like strengthening of the connection of computer vision and machine learning, and that was made possible by neural networks. And this is as kind of introduced like a game change. So at the very beginning, all the image analysis, image processing, and even image classification algorithms were based on mathematical and statistical modeling of images. So there was the scientist, the researcher, the engineers, whatever, who believed to find a good model that was able to describe the image. Okay? And then based on this model, was designing algorithms for solving a given task. For example, you can assume that your image in the DCT domain, a small portion of images can be represented as like a few coefficients, because This is actually what JPEG is built upon. And everything was, say, built on some mathematical modeling of this kind of mathematical model. Now, with the advent of machine learning and deep learning, this has kind of disappeared. And images are even more, most often handled as kind of inputs to this black box model. In any case, it's worth to know very well in order to use these models over images. It's necessary to know very well, say, the image processing basics. And of course, yeah, this is what I was telling you. There is an increasing interest. Okay, very good. There is an increasing interest over the deep learning. So, and if you plan, so this is just, if you plan to pursue in the future kind of research-oriented career or even a computer vision, a career in the computer vision, you have really to bear in mind that this is like a field which is increasingly where the interest and the research activities are increasingly growing. This is the number of articles being published over the past few years in the AI-related domain. And you can see even in the jobs related to computer vision, there is an increase. So it's kind of here. So it's not like the keyword autonomous driving, which has terribly grown. Like, of course, it's the new thing, like more general keywords like machine learning, neural networks, visual image recognition are also all increasingly growing. So this is kind of, I can tell you. So this is definitely both for you to take this course if you want to take a kind of research-oriented career in the future, or if you plan working in certain domain where like automation given by image understanding algorithms and the models, it's kind of growing. So now, after this like kind of overview, which would have been even nicer if we were able to play videos, let's step back for a while and try to see how to handle images for solving the image classification problem. And in this lecture, I have to introduce a few like basic notions, right? And the first basic notion is what is an image? So how it is represented an image over inside a computer. Okay, like in the file you have where it's, I don't know, bazaar.jpg, this picture, in this figure. So what is the information written there in that file? So because these, when we want to design whatever neural network, whatever deep learning model, you have to be very aware of what kind of input you are handling. And if you take these photos, this is an RGB image. So most probably these notions are known to most of you. But I mean, if someone has not these things, but if these things are not very clear to all of you, then it's worth spending a few words on that. So maybe it might sound as trivial, but this is something you need to know. So an image, it's written as like a three-dimensional array which contains like real number. In practice, when you feed to a neural network, it's going to be like most often real numbers, so floating point numbers, which has like two special dimensions, and the third dimension, which is the number of columns. So these images are row, C columns, and three color channels. And the three color channels are three grayscale images. Each of these grayscale image, it contains the information on how much red, green, and blue is in the image. You can see this image is very reddish. You can see that the red image here is much brighter than the blue image here, because there is very little blue here in the above image. And if you zoom like to the images, this is something you start seeing the pixel, like Minecraft, right? And each pixel is actually corresponds to a number, which is between 0 and 255. I mean, it's a char. It's a unit 8, whatever you want to call it. So 1 byte. So 1 byte per color channel per pixel. And 0, it's black, 255, it's white. And of course, 120, it's kind of gray. So far so good to anybody. So very simple. So we are going to handle like 3D. If you want to perform image classification, the input of our classifier will be this kind of matrices, three-dimensional matrices. And for example, if you take this pixel here, right? So that pixel there has the color 0, 205, 155, and because it's very green, so it's one of the most green area. You can find also the reddish part of the image here. You see it is 253, almost 0 the other, because it's like totally red. The white, it's up here. You can see that all the three color channels are close to 255. And here is, okay, that was the blue, and you can see the black. Here, all the three intensities are like kind of very low. So this is the way you combine color, the sum of colors, right? By these three triplets. And there is the green because the human eye is more sensitive to the green than to the yellow. So because in the primary school, the colors were red, yellow, and blue. But in the RGB sense, in the camera sensor, most often this you get are red, green, and blue. The most spread. And so when you will open this in MATLAB, in Python, if you take an image, there is a command in read, you will have like these three matrices, which you can crop out of your three-dimensional image at the very beginning. Okay? So, okay, now let's see what is a video, because the network I was showing you before were able to process videos even in a frame-by-frame manner, indeed. And so a video is nothing but a sequence of images. So if you are given an image, so this is an image, right? A video, it's like a sequence of these images over a third, stacking an additional dimension, which is the number of frames. So when you see a video which is like 20 frames per second or 30 frames per second, even in this like tiny video, which is 144, 180, which is definitely way smaller than the videos we are used to, you can see that you have like this number of pixels, right, times this number of color channels times the number of frames, say 30, per each second. And since each pixel contains a byte, this becomes like this second of a tiny video becomes almost 400K bytes. And so if you take a video in full HD, one frame is going to be 6 megabytes. 1 second at 24 frames per second will be like 150 megabytes. Of course, videos are typically smaller. The videos you record from your phone are not like 150 mega per second, correct? And this is because the information on the videos, like on the images, it's kind of very redundant. Yeah, I'm using C, the number of columns. So a video, it's there an image, are rows, C columns, then there are the color channels, which is 3. I'm not using a letter for that, and then there is time. So I'm telling you this story for two main reasons. So from your experience, when you record a video from your phone, full HD video, it's not as big as this. Maybe I might be wrong with the calculation, it might be approximated, but this is the range of number of bytes you need to store kind of this video. So if the video takes much less, it's because it is encoded. And if you can compress it a lot through encoding, whatever kind of encoding you use, MPEG, it means the information is very redundant inside the video. But, and the same for an image. when you start feeding this kind of data to your neural network, to your machine learning model, they are not compressed, right? They are like kind of expanded into matrices which has the same size of the input. So 150 megabytes, 1 second. So this is not possible to feed such a large input to a neural network. So all the networks we will see, for example, is not yet possible. Cannot be take like rather small images. So the first where we see are meant for 30 by 30 images, 30 by 30 pixels, and so on. Because even if they are like very small, when you written like in JPEG, this dimension explodes when you open them and you place them in the RAM of your computer. This is not something you have to forget about, because we will see through convolutional neural networks most probably tomorrow that, I mean, there is a terrible increase in the memory requirement when you're processing an image. So of course, I mean, I don't have much time, but because and that this is not essential, but you can understand that there are like even higher dimensional data than images. So for example, in hyperspectral and in multispectral and hyperspectral images are using the remote sensing in order to analyze, for example, the Earth from like a satellite or from aerial pictures. Maybe you got more color bands. And by analyzing different color bands, you can understand what is the content of the soil, like if there is water, vegetation, or like roads, whatever, or buildings. And of course, then you can have also volumetric data. So data that are constructed, not live on a plane, like an image, but are like an MRI scan. So here, and of course, also in these models, these models are now, sorry, this kind of data are being processed by neural networks and deep learning model. And here there is a third dimension which makes things more complicated, right? Because you have now, your input is a cube, which is even like 256, which is a kind of standard size for the MRI. So this becomes 256 power 3, which is a lot of data. And okay, so we have seen the input images. Now you are very well aware of what we are going to process. Indeed, high dimensional data, high dimensional matrices. Now let's jump to a different topic, which is like the basic transformations we can do on images. And this is, I mean, necessary to know, and you have to know this very well, because otherwise you won't understand any following. You won't understand the convolutional neural network and any other following topic we are going to see. So in general, we are given an input, I, which is my image. I can define a transformation of the image as like this T, which transform my image, it's a function of my image and provides me another image. And in general, what I'm expecting is that this transformation transform my image by analyzing each pixel in the input, sorry, and I can use the whiteboard. So you're given an image, and you want your transformation to give you another image as output, which is what I'm calling G, which is another image. And in the most general case, my transformation will operate by taking a pixel. So this is not the most general case, but the most general case we consider will operate at each pixel by selecting a neighborhood, a region. So this region is called U. And if you take this pixel here, I don't know, R and C, you can get an output value here which is G of R and C, and these will be a function of a small spatial extent around the same coordinate in the input.
Sorry, Prof, can you turn on the light of the blackboard? Because I can.
Sure. Just need to find them.
Thank you.
You're welcome. Voi sapete dove sono? L'ultimo? No. Ah? Prima di provarli tutti. Okay, grazie, thank you. So the point is, the most general transformation we can think that we will consider here, it's a transformation that takes for each pixel where we want to define the output a small portion, and like the simplest general transformation we use, it's a linear transformation, of course. So the output G of my image I in a given pixel R and C is going to be a linear combination. If it has to be a linear transformation, this is going to be a linear transformation over a certain neighborhood U, let's say X and Y belonging to U, of weights, let's call it WXI, times the input value of R plus X, C plus Y. Now, this seems extremely complicated, but it's super simple. So when I say X and Y belonging to U, it's like you define a region. Most often it will be a squared region indeed. We are not designing like square shape. So in practice, it's going to be something like this. And all the coordinates falling here will correspond to our neighborhood. So you will have X and Y, which can be, I don't know, 1, 1, 0, 0, 1, minus 1, minus 2, 2, whatever. So you take the sum over all these indexes of some weight, coefficient, I'm getting back to this in a second, plus these are just the image values selected around the center, R and C. So it's going to be R plus 1, C minus 1, and so on. Okay? I'm not entering too further into these details because then you need to define, say, the coordinates. The coordinates are typically written flipped in the image. This is not something that we need, indeed. But because you got rows which are increasing like this and columns which are growing like this. So this is just to explain what's going on here in this expression. We are just taking a bunch of values around your center, R and C, where you want to compute the output, right? And this is obtained by this expression, right? The sum, so these values by varying X and Y. Just shift a bit your values next to R and C. And here, since I want a linear transformation, I want these weights to be, I want this, I take a linear combination of all these values. So far, so good? Okay. And now, in general, we say that these weights does not depend on the specific location. I'm going to use the same weights to hold the image for this transformation. And this means that I can build up what is called a filter, or that contains all my coefficients. So like in a 3x3, in a 3x3, in case my neighborhood U is just a 3x3 range, I will have that these 3 by 3 matrix contains all these weights, and this is going to be like W00, this is going to be W11, this is going to be W1 minus 1, 1, whatever. Okay? And now, if you apply the very same operation over the whole image, you get what is called the correlation. So you take your input image, you want to define the output in a given pixel. What you do, you take this weight, you overlap them, you bring them over the input image. Guys, if you don't understand this, don't even try to implement a convolutional neural net. Okay? Really, uninstall Python. So this is very important. Okay? So this is going to be the basic operation you are going to perform to all your images. So if this is like the center, this is the pixel where I want to compute the output. You select a neighborhood, like this is the neighborhood of the image. You overlap, like ideally the weights. You take this weight, you multiply times this pixel. Take this weight, you multiply times this pixel, and so on. And then you sum them all together. So this is what happens in this illustration. This is the image. You overlap, sorry, this is the image. These are the weights. You have to imagine you have to overimpose the weights to the image, compute element-wise product, sum them all. This gives you the output in a single pixel. To compute the output over the whole image, you move this pixel of 1 pixel left or whatever, right? And you repeat the operation. So the same operation is being applied, and it's a linear operation. Is this clear to everybody? Please. I can take, so the question is why I'm selecting a region and not just a transformation of single pixel, because a transformation of a single pixel would be just an intensity transformation of your image, like increasing or decreasing the brightness. If it is linear, it's just a matter of rescaling, say multiplying an image times lambda. This is not very informative. What is more informative is to mix pixels together. No, this is in general. I mean, I'm talking about correlation, which you can find even in more general settings, not just in these. I mean, even in computing, say, the autocorrelation between two frames, or you can find, say, in a plethora of applications, in images. But the most general formulation is that you have a filter which describes your operation, and you apply this very same operation, which is written as the sum, to each pixel. So the input of your transformation is going to be the image. The parameters of your transformation are going to be the weights, this matrix of weights. Of course, yeah, but the transformation, in that case, you would have like one image, which is one frame, and the weight, which is like the other frame. So they're using the second image as a weight. Please.
Yeah, can you also repeat the question, because from home we don't hear anything.
Sorry, I didn't understand. Please, but if you have to ask a question, you want me to repeat the questions?
Yeah, from the colleagues in the room, because we don't hear.
Yeah, sure. So he was asking whether this is related to the correlation between two consecutive frames, and then you heard the answer. It's like, instead, this is more general, because the most general settings, you are transforming an image, which is the input, by this formula with weights given by this matrix, the filter. And
Sorry, Professor.
please.
Can you write a little bit thicker on the blackboard, if possible?
So it's
if you can write with the thicker lines, because I cannot
thicker.
see very well.
Okay.
Yeah.
Okay.
Thank you.
Okay. You're welcome. Sorry. The linear operation is this. So the question is, I talk about linear combination. Where does this come from? And the answer is, by definition. I mean, I can take whatever transformation of my image, and I can transform each pixel in a nonlinear and different manner. But I decided to restrict my analysis to linear operations, which in my case are being applied the same through the whole image, right? And so this is correlation. So the question is, is there a connection between these and convolution? The answer is yes. You were already saying what is the difference is that here is a plus, in convolution there is a minus. And now I'm telling you why I'm talking about correlation, and then you will understand. I mean, there is no particular reason to talk about convolutional neural network and not correlational neural networks, because the filters are because these matrices are being learned. So, I mean, but now I'm telling you why we need to talk about correlation. And here you are. What is going to be the output of the correlation between this image? So this is going to be the image, and these are going to be the weights, W. And now assume that the image is binary. So 0 is black, and 1 is white. So what is going to be the output for you? So the output is going to be an image, right? What your colleague is saying, which is brightest. The highest value is going to be in the location where the weights actually overlap perfectly to the input image. And the reason is, so this is going to be the output, except from some shift. And the reason is, and you can see the same here, this is your image, and this is the weights. The output is going to be brightest where these weights perfectly overlaps to the image content. And the reason is that, just imagine you have, so this is your image, these are the weights. What you have to do is to like visually overlap the two, okay? And now you have like either 0, 0, 1s, 1s, whatever in the weights. And of course you have the same, you have other values in the image. And of course then you are computing the element-wise product and summing them all together, right? And this operation actually means that the sum will be like the sum of the pixels where both are equal to 1, right? So if here there are like 100 pixels that are that are white, the output cannot be larger than 100, and it will be equal to 100 exactly in the location where the template, where your weights overlap to the image, which is here. So that's why I'm not flipping the filter. Because if I would have flipped the filters, right, this wouldn't be true. There won't be like a matching between the image and the weights, correspondence. Is everything clear? Is this clear to everybody, guys? Why the maximum value is here, why not here? Because here, the output will be, if you overlap n0, n0, n0 here, you perform element-wise product, and one of the term is always 0, you sum everything, it becomes 0. As you move and you start overlap, for example, here, there will be 1, 0, for example, that is overlapping to the other, and there will be some small value which corresponds to the number of ones that are overlapped. So the correlation, the stronger the correlation, the more similar the weights and the portion of the image are. Correct? Is this clear to anybody, to all of you? Okay. Now, of course, there are issues. So this is not going to be a perfect detector. So if you want to look to detect something, and now I give you the swapped template, the swapped image. Of course, you have the maximum here, but also the maximum in all those regions, like this one, where you overlap your template to a region which is Y. So this is not going to be the best possible way of finding out, of performing template matching, but still, through some normalization, and probably this is the reason why we use normalization also, we can solve this problem. But what I really want you to understand is that through this linear operation, which is applied the same through all the image, what you get is that you spot those regions of the image that are most similar to the filter, to the weights. Correct? Perfect. So let's jump now. So we have formulated, we have presented the basic operation I need to introduce, convolution. I've presented the images. Now let me introduce which are the tasks we are going to solve. And the first task is the image classification. The image classification is like standard classification from a neural network, but the input will be an image. So you will be given an image I as input, and what you will get is that as output, it's like a label, which in case of images, these typically correspond to the name of the image itself, because the classification problems being addressed over images are typically contains a lot of classes. We are in the order of hundreds of classes for images classifiers. So you can see wheel, cars. I mean, of course, this is like a categorical variable, but typically it's like you use the name. And of course, I mean, we see as output, we see the label, but indeed behind the classifier should provide me a score or a probability, which tells me how confident the classifier is to provide that image to belong to that class. So for example, here it's saying that this is a wheel with 65%, but also a tire with 30%. So the image classification problem being formulated, it's train a classifier which takes as input an image and provides as output a categorical variable belonging to a set lambda. And the set of lambda of like the classes for the images has to be defined a priori. I mean, this is what you see also even when you take like a toy example in training a neural network. This is exactly the same, but now the input is an image and the output is just as before a label, and the label corresponds to the content of the image itself. Okay? This is the image classification. And this is something you have in your phone, like wherever, if you type, if you go to like Google Photo search or similar engines, if you type rabbit, for example, in my Google Photos, this is the pictures were returned to me. So these images can be well classified as kind of containing a rabbit. This is a rabbit, even in a weird position. This is wrong. It's not a rabbit, it's a tanuki from the Japanese mythology, whatever. Sorry? In Google Pictures, yeah. Google Photos, sorry. Yeah. This is, and of course also the other one contains a rabbit. So classification, the problem is clearly formulated. Take an image, provide a label belonging to a discrete classes. Localization, it's a different problem where you are given an image and what you get as output are 4 real numbers plus 1 categorical quantity. And in this case, like it would be, so this is one class label. But on top of the class label, you got the coordinates of the bounding box containing the object. So in this case, you would have x, y, w, and h, which corresponds to the x and y coordinate of the top left corner, and w and h, which are the width and the height of the bounding box. Okay? So this is image localization. So the input is going to be an image. What we want as output is a tuple of 5 elements, 4 real numbers, 1 categorical name. Object detection, it's something like very different because, I mean, intuitively it's like the same, but the model becomes much more complicated because you want to have the bounding box associated to each object in the image. So the number of output associated to each image is not going to be fixed. It's not given a priori. I give you a picture with a picture of you now. I want my object detector to return about, I don't know, 20 labels as person. If I shoot a picture of the whiteboard, probably it has not to return any label. So you have an output which has a variable length, a variable size. So given an input image, you get as output a set of tuples, and then each one contains the bounding box and the label corresponding to what is contained in the image. So far so good. So we have seen the basic problems: image classification, image localization, object detection, image segmentation. Image segmentation instead corresponds to the problem of associating to each input image like a false color image, like an image having the same size of the input image, but whose values, the pixel coordinates, are actually values of the labels. So in each pixel here, displayed in false colors, like red is person, each pixel is red if in that pixel that pixel in the image belongs to a person. The same for the dining table and for the boat, which are not there. So there is an error here in this automatic classification tool, but that was like a kind of strange image, okay? And of course, you have to consider also a background class, which contains everything which is not related to the categories you want. So from image segmentation, what you want is that given an image I, you got an output image which is S, which has the same size, spatial extent of the first image, but contains only values that are related to the categorical, so that are the labels, right? And now here you can build any other problem over this, like instance segmentation, which means that you want, given an image, what you want is to find out bounding boxes corresponding to each object, and then on top of the label corresponding to the bounding box, like here, you have like elephant, you have person, 3 persons. You want also to know the mask. So inside this bounding box, you want to construct a binary mask where you have 0 out of the to those pixels that do not belong to the category, you have associated to the bounding box. So a binary mask which tells 0 out of the person and 1 inside the person. So the output is going to be the bounding box coordinates, the label associated to the coordinate, and the set of pixels or the binary mask associated to that label inside the bounding box. And this is something you have like customarily in your phones or in your cells. So we have seen what images are. I've introduced you the basic operation over images, which is correlation or convolution, we will see in a while. And then I told you all the problems, say, kind of relevant problems we are going to solve in these, we are going to see in these lectures. And now let's start to think like the first image classifier, right? So how to train a simple image classifier and whether it will be successful or not. But first, just to figure out whether this is a challenging problem or not. So say with respect to any other classification over descriptors or vectors you have for images. So you have, say, in traditional machine learning problems, is image classification a very difficult problem? And the answer is yes. And the first reason is that is the dimensionality. So this is the Cypher-10 dataset, which is like a kind of toy example dataset, which was proposed in 2009. So 2009, it's really Roman ages of the Roman Empire, considering the growth of deep learning. That was before deep learning, indeed. And the problem was to classify very tiny images, 32 by 32 pixels, not even an icon on our phones, and color, and in 10 categories, very different, like automobile, say plane, airplane, bird, cat, whatever, and 6,000 images per class. Okay, now and that was a kind of challenge to classify these images, and the challenge was, in particular, given by the dimensionality, because each input was 32 by 32 by 3, which is about 3K. So that is a zoomed image, 32 by 32. That should be the input of your classifier for which you want to associate the label, track, whatever, and the input contains 3K pixels. And at that time, like the standard repository for machine learning, which was not Kaggle, was UCI, the machine learning repository. Only like, say, almost 90% of the data sets, annotated data sets, had less than 500 attributes, because people was not classifying images. And only a few of these data sets, like 8%, had comparable dimension. So having like data set of very few data sets of such a dimension means that there were not many classifiers able to handle them. So the first one is the dimension, and this is something you have to bear in mind. I'm getting back to the initial consideration over videos, over images, that the actual size of your input, when you feed them to a neural network, are going to be measured in this, like in the number of pixels. So you expect a real number, floating point number to express each and every pixel, so 3000 floating point number. And then, say, in normal images, there is kind of label ambiguity, which means that a label might not uniquely identify the content of the image. So while the input, typical images, contains multiple objects, and as a result, you don't have a unique label identifying the image, and this is a problem. For example, if you take this picture, what would be the actual label? You can say that there is a man, there is a beer, there is a dinner, there is a restaurant, there are sausages. Just assume that your classifier have to make a distinction between man and the restaurant, or beer and the restaurant. You see, this is, if you label this image, you are going to associate a single label to this image most often. So just man, or beer, or whatever. But your classifier, a good classifier that is being trained, can see other labels associated to the image itself. So there is a label ambiguity. Dimension is the first issue, label ambiguity the second. Then there are a huge amount of transformations that are completely natural to us that does not change at all the image content, does not change the label, but they do change each and every pixel in the image. Take, for example, these 6 pictures. The content is exactly the same. I was not moving the camera. The camera was still. I was just changing the lighting conditions. Opening the window, closing the window. Now, I don't know what kind of label you can associate to this image. Toys, train, horses, whatever. But you can see that all these inputs have to be associated to the same label, but they differ in each and every pixel. So the similarity between the images, it's completely uncorrelated from the similarity between the content from the label similarity. Then there are deformations. For example, you take all these images refer to the rabbit, right? But the rabbit itself is in a very different position. It's even being deformed by a forestal guard in the first picture. And again, don't think at the images that we see with our eyes, this is what we would do. Think of a classifier which can just take as input a matrix containing the color information behind this picture. Viewpoint changes, all these are a statue just depicted from different point of view or just with minor, or say very similar statues, but again, all the pixel changes. And then on top of these, there are like thousands of other issues like occlusions. Everybody has no problem in saying there is a cat, but you can see how little portion of the image is related to the cat. Even the rabbit is kind of occluded by the grid. The content can be mixed with the clutter, like in this case or in this case. And there are like scale variations. So in both cases, you would say there is a man holding a laptop, but you can see that the relative proportion of the man and the laptop actually changes a lot. Then, also, why image classification is challenging? Because even inside the same class, there is a huge variability. So take, for example, all these are chairs, and all these are rabbits, but you can see how much even the peculiar features of the chairs and of the rabbit actually changes. Look at the ears of the rabbit, look at the color of the rabbit. They are not like distinctive on the class itself. And the same for the chairs. There are even chairs which do not even have like 4 legs. And the other problem, which you can see when we want to classify images, is that while for traditional, when you want to train a classifier for vectors, like say a vector of real numbers, of measurements, like the weight, the height, and some other measurement from a person, you might expect some correlation between the distance between vectors and the distance like in the label space, such that if you compute the difference between vectors, this is going to be meaningful. So vectors that are nearby would correspond most probably to labels that are the same. This is not the case for images. And I'm running out of time, so I'm not giving you this example, but I'm not giving you this example in detail. But now, just consider this experiment where you measure the distance between two images, image 1 and image 2, and you do this as illustrated in this picture by subtracting the two images element-wise, okay? And here, and computing the absolute error, the absolute value of the difference, like 56 minus 10 gives you 46, 32 minus 20, 12, and then you take the norm, or you sum them up, and you got like a certain number, which is telling you how the two images are far apart from each other. Of course, the smaller, the closer the two images, the larger, the largest. And this is like what you would do if you train a nearest neighbor classifier, just to associate to each image the closest one. Now, if you take these three images, these, and these, they are at the same distance from the one at the center. So if you measure the distance as I was illustrating before, like, so this is the image 1, and this is image 2, this is the norm of image 1 minus image 2. And there is the same distance with image 3 and image 4. And of course, this is a bad news, because if you measure differences in your input images, as you would do for using a traditional distance for vectors, we are not getting something that is related to the perception we have over images. Because this image, for example, image I3, it's exactly the same as image 1, but slightly displaced. While image 2 has darkened the eyes and the mouth, which are like the distinctive properties for recognizing a person. And image 4 has just been slightly dark. So this means that when you want to classify images, it's not just enough to take as input the pixel, the input similarity, the input difference between the images is not meaningful to predict what is the content similarity. And if you take now, for example, the Cypher 10, that data set, and you try to place images, all the images, all the 60,000 images over the plane, according to TSNE, I don't know whether if you ever heard of this, but it's like a visualization techniques that place nearby samples that are closer according to a given distance. And now you try to do this by saying, hey, put nearby images that are nearby according to the distance which we have been defining before. Then what you have is that, for example, this track, this frog is most similar to this track than to this other frog. Okay? And there are plenty of these issues where you can find, like, this horse is closer to this bird than to this other horse. So if you want to handle images and you want to extract some visual content of the image, some label associated to the perception we have of their images, we have to forget about traditional techniques that were measuring distance between inputs based on some like Euclidean metric or whatever, because this does not correlate with the perceptual similarity. Okay? And And here you can see, if you go through the slides, you see what I mean, it's just, if you implement a 1 year's neighbor classifier, which is exactly the same as measuring this distance between images. But now, okay, I told you that that's a challenging problem, but let's try, in any case, to train a classifier like a neural network over each image. And like a classifier that takes as input an image and provides us as output a label related to the class where the image belongs to. But instead of using a neural network, I'm making like a step behind, and I'm taking a linear classifier. So a linear classifier is nothing but like one layer of a feed-forward neural network, but we don't put the nonlinear because we don't need it. We have just one layer. So here is what happens to our, let's take a linear classifier. I can write at the whiteboard. Sorry? Yeah, but in order to do this, I should, because I'm recording from my PC, I cannot record from this, I cannot record from this. So it's, I can write it here, but yeah, the recording there is a small, yeah, I know. But I don't know how to solve this problem. He can do that. Then I will ask him for the next lecture. Okay, so now the point is that we take as input an image. In this slide is called X, and my image X is going to be represented as a vector, the vector you can see here, right? So my image has 3 color channels, red, green, and blue, okay? And I'm like unrolling it this way, such that in the first positions of the image there are the red pixels, then in the first position of the vector, in the topmost positions of the vector, there are the pixels, color, the red component of the image pixels, then the green, and then the blue. How it is represented exactly here in this illustration, right? Okay? Then, if I want to take a linear classifier, which is actually what happens when you take one layer of a feed-forward neural network, it's like I'm defining some matrix W, which has, so if these are n pixels, this matrix has n columns, okay? And the number of rows of this matrix is equal to the number of classes, so the cardinality of lambda. So in my case, I want the classifier to classify in only 3 classes in this illustration. And so this is the most general linear expression I can compute, the most general linear transformation I can compute of my input, but I have to include also an additional term, okay? So my classifier is going to a bias term, Wx plus b, where x is of dimension n rows times 1, W has 3 rows and then columns, and beta has 3 columns. Is everything okay? So this is the most general linear transformation I can compute out of an image, which is a vector unrolled, which is unrolled in a vector having n samples. No, wait. This is like, you compute so the question is how to use the bias. And the way you compute the bias is the way you use the bias is the way you use the matrix product. So here is row times columns product plus the bias. So this is related to first row times columns, and indeed, the output, what you have in the output, it's just score, vector, whatever, which is the score of the class dog, the score of the class cat, and the score of the class rabbit, whatever. How would you represent this in a neural network? There is no softmax neuron. I have not placed the softmax neuron. Sorry. One hot encoder. Well, this is going to be a neural network that takes as input. What would be the size of the input of your neural network? No, what is going to be, so this is a linear classifier, and I mean, you can believe this is, so I hope you believe that S equal WX plus beta, where X is your input, W and B are the parameters, and S is your output. This is the most general linear expression you can write from X. Is there a question? Here's a question. Don't be shy. Ask a question. Is it okay? So, if you want to write this as a neural network, what would be the input layer? So can you speak louder? It's one layer of a feed-forward neural network. So the input size is going to have like how many neurons? The size of X, n, right? So n rows, one column. So n neurons. How many outputs? So how many layers? One. Okay? How many output neurons? The number of classes, 3 in my case. Perfect. Right? And now, where are the weights of the first row? How would you represent in the traditional neural network representation? By the weights connecting this guy. How many are these weights? Yeah, but this one, how many are n? This one are n weights, right? So the weights associated to the first output neuron are n plus 1, the bias, right? And this is because if this is the input, what you do in a neural network, you compute, now maybe the notation is different from what Matteo was illustrating you, W1 I, for I that goes from 1 to n, xi, plus B1. Is this the same notation, right? So this is the most simple neural network you can train if you want to classify your image into 3 categories. And I'm not placing the softmax just for the sake of illustration. The softmax doesn't change much because And now I will tell you why. Here, and I'm not even placing a nonlinearity. And this is because then the interpretation will be simpler. Okay? So you have to take this as a linear classifier, which corresponds to like a one layer of a neural network without nonlinearity. And the second weight here, so and this neuron will tell you kind of, in principle, the probability for the input to belong to the class dog. But this is not going to be a probability because there is no softmax, so it's going to be a score. And the higher the score, the better, because the softmax, what doesn't change the ranking between the output, right? So this is the score associated to the class dog. This is a score associated to the class cat, and this is a score associated to the class rabbit. And each row of this matrix corresponds to the weights for each associated to each output neuron, plus the bias. So far, so good for everybody? Okay.
Sorry,
Now,
could you repeat again why we have n neurons?
why we have n neurons in the input? Because the image has n pixels, actually n pixels over the 3 color channels. So X is belonging to Rn. And the output, it's as dimension 3, because we only have 3 classes in this illustration. Okay? Is it clear?
Yes, thanks.
You're welcome. So now we can train our neural network using a training set. And by training this neural network, what we will consider is that we use as loss something that is considering a correctly classified label when the score of the right label, the highest score provided as output correspond to the true class. And by using a training set of annotated samples, and by using this simple loss, we can define what are the weights of this matrix W plus the bias. Right? This is not surprising.
Professor,
This,
why is the input image a vector with one column?
the image is just one column, because if you want to feed to a class, so far you have seen just classifiers that are like feed-forward neural networks, right? Or whatever classifier you have seen so far. So that is an important point. Thanks for the question. Whatever classifier you have seen so far, it's a classifier meant to classify a vector. So if you want to take your classifier to classify your image, you have to bring it to a vector. And the way I bring this to a vector, it's like illustrated here. You unroll your image, each channel kind of column-wise or row-wise, doesn't change much. So there are no alternatives so far on how to classify images. You have to bring them to a vector and then train your neural network or train a linear classifier that in these simplified settings are actually the same. Any question? I see you're skeptical.
Thanks.
Do you have a question? It seems you are skeptical. No. He is skeptical. You are skeptical. Why? Yes. Because you have to unroll the image in a vector. You have to unroll the image in a vector, and I'm unrolling them like column-wise for each channel. Please. Well, in some cases, like you have to consider like the cipher. You have to distinguish between plain and deer. One is going to be over a green background. The other one is going to be over a blue background in the sky. So of course, you have to consider colors jointly, because that is definitely useful. And we will see that this is what the classifier learns. Now I'm going to tell you what the classifier learns. I'm using this overly simplified model because this is kind of interpretable. Okay? And then I will go back to the correlation, to what I was telling you at the very beginning. So now, assuming we have trained our classifier to minimize a loss, which is a classification loss, you can take a margin such that the highest score corresponds to the correct class, and the lower score and the other scores are lower than a fraction. So you can train this classifier with your favorite algorithm and with your favorite loss, and at the end, well, let me jump directly. Once you have trained it, you have your wonderful parameters, which are W and beta, and you can have a look at them. So let's see what the classifier has learned. Now, as we have seen here, each row of my matrix corresponds to a class, to an output neuron. So if I want to see how my image is, the score, say, for my image to belong to the class dog, I just have to look at the first row. So far, so good. Okay, the first row of my matrix W, because these are the weights associated to that output neuron, if you look at in a neural network notation. Now, this means, so what this classifier does, what you have been learning, it's actually a function. Say, take Wi, which is the ith row of the matrix. So this is W1, this is W2, and this is W3. And you have learned a function that does Wi times x plus beta I. And this is telling you the score for the classifier to belong to the ith class. Now, this is a linear expression, right? And if the pixel had only 2 pixels, the image had only like 2 values, that would be x1 and x2. W would be 2 values, like A and B. That would be plus B1. And this is actually the equation of a straight line. Well, it's the equation of a straight line if you set it equal 0. So this is going to be Wi x plus bi equals 0. So it's like you are taking your space where images live, and you are cutting with an hyperplane, which in 2 dimensions is just a straight line, and you are placing on one side all the samples that are providing you a positive score. So you would expect all the dogs to be here, and the non-dogs to be here, correct? And if you are taking 3 classifiers, or 10, say if you are classifying over 3 or 10 classes, this means that you are cutting with many hyperplanes. All these hyperplane is taking samples belonging to the corresponding class over one side, and all the other on the other side. But this space, which is the plane here, indeed, is not R2, but it's going to be Rn, where n is the number of pixels. So it's a very high dimensional space. In our case, it's 3,000. So this classifier is just trying to cut the image in the dimension 3,000 with hyperplanes, all the samples on one side, for a given class on one side, and all the other from the other side. And this is one interpretation, and you see that it's kind of, we know that this is kind of poor, because the distances, as we mentioned before, in this space, are not very relevant depending on the image content. But let's see how to let's try to visualize what the classifier has learned. And let's take this row, W1, correct? And each row has n pixels, right? And n values. So I can reshape these values, right? I can reshape these values and bring them to a matrix. Or better, sorry, bring them to an image. This is possible because this is an image, and this has the same size. So I can take these and roll them to have the same size of an image. So I will take the first parts of the weight, and I will bring them to the red channel of an image. The second half to the green, and the third half to the blue. The third half. Okay, the first portion to the red, then green, and then blue. So if you reshape these are the images you would get by reshaping the weights of your matrix. And this is what the classifier is doing, is taking this row, multiplying times this vector, means taking this image, W1, which is this row reshaped as a vector, and it's multiplying them times your input image. So if you want to know how close what is the score for your image corresponding to the plane class, well, all that you need to do is to take that image and perform an element-wise multiplication, and then summing all the pixels between that image related to the plane, the learned image related to the plane, and the input image itself. This is exactly the correlation, where the image and the weights have the same size. Overlapping the two, computing the products, summing them all up. This is exactly what happens when you have like computing this row times this row column product. This is exactly as overlapping the two images, computing the element-wise product and summing them up. So, and this is a filter. Now the filter is going to be, you want to know the score of your image to belong to the plane class. All that you do when you train a linear classifier is to identify this template, and you compute the correlation between the template and your input image. And the higher the score, the more likely the image to belong to that class. So you can see ship and the plane are very similar templates. And what are they learning? The only things they are learning from the ship and the plane classifier is that you would expect a lot of blue in the background, and in the case of the boat, some white region in the middle. So the higher the score means that the image resembles most to this template, more than the others. And the same for the plane. You can see the template for the truck, for the car. Actually, the template for the car, it really resembles a car. And you are associating the label car, when you train a neural network for classifying the images, if you exclude the softmax, what you are learning, it's a reference template to be correlated with the image. which provides you the highest possible score for that input. And it is red because probably in the training set, there were mainly red cars. And of course, you can think of these, like the deer, you can see it's green, the background, and the center is brown. And this is a perfect classifier. I mean, because if you take this to be the plane classifier, and this to be the deer classifier, the first one is very blue. Being very blue means that here it's close to 1 or 255, whatever. And the others are almost 0, right? And of course, when you feed an image that is like very blue, there is a lot of blue, the response will be very large because you are preserving it. While on the other classifier, the one on the deer, there is a lot of green, and the other colors are close to 0 because, you see, the background is green. So this means that you are actually considering an image, so the score for the deer class will be higher when there is a lot of green. And you can see this from the template. Again, think of the template matching problem before. Yes, yes. So, yeah, so I repeat the question. So she's saying, training the image, I get my weights, I reassemble the weights into a matrix, into an image. This image is being regarded as a template, and what the score computation does, so what you do when you compute the score, it's actually computing the correlation between your template and the input image. And you can see why the template is like this. It's green because you want the image to be very green there in the background in order to identify a deer or a bird. And instead here it's blue. But you can see the details, you can see the horse, which has 2 heads, looks like a horse having 2 heads. And this is because probably in the training set, the head of the horse were sometimes left and sometimes right, and sometimes right. Okay, so of course, this is the best you can do by training a neural network, a neuron of this, or say a layer of a neural network. And it's like comparing the images against this template. And this is not enough, definitely, for performing the task we have seen so far, okay? Or the task I was mentioning. And tomorrow, online, I will give you the basics for understanding the actual solutions for performing classification of our images, and in particular, we will see the convolutional neural network. So stay tuned on the correlation or the convolution, whatever, because tomorrow everything will be built up on these topics, okay? Sorry, I have to conclude. I have the other colleagues of yours to. Bye, sorry. This is terrible for listening. This room is kind of. Devo lasciarti. Ok. Ok. Sì. Veloce.